A rectangular timber beam AE has the cross-section area, dimensions and the loading as shown in figure. We have given here overhang beam. We have support at A and D. At point B, we have one point load is acting equal to 12 kilonewton. At pre-end, we have 8 kilonewton. And the section here is a rectangular section. For rectangular section, the maximum bending stress at the top and bottom is same. We are interested to know the flexure stress distribution on the cross section at point C. So exactly at cross section C, we need to find out the bending moment. So to find out the bending moment at point C, first you have to find out the reaction at A and D. So what we'll do, we'll only find out the reaction at point A and we'll cut the beam. And since no load is acting at point C, whether you take the left side or right side of the C, the bending moment values remains same. That is our procedure. So exactly on the symmetry axis, we have the centroid location. Let's represent equal to G. This time the top fiber and bottom fiber has a equidistance equal to 100 mm. Let's say we have B is equal to 100, D is equal to 200. Moment of inertia is BD cube by 12 and the distance of the top fiber and the bottom fiber is same. But since we are setting our axis at point G, where we have Z axis is horizontal and the vertical axis is Y axis. So point P will be above G will be taken as positive value is 200 by 2, that is D by 2. D by 2 is same as equal to 100 mm. And for point Q, that is the bottom fiber, you have to take the negative value of Y, that will be D by 2 again, but negative value is minus 100 mm. And the value of I, that is Iz, will be equal to BD cube divided by 12. And the bending stress will be either on the top or bottom, will be sigma equal to minus m by I into Y distance. Now before this, we'll find out here what is the reaction at point A. So let's say reaction at point A is equal to AY, reaction at point D is equal to DY. We are interested to know the value of AY because this one is a simple solution. So what we'll do, we'll take the sum of moment of all forces about the support D, and we assume the sign convention, that is a clockwise moment is positive and the total sum must equal to 0. Moment of AY about point D will be clockwise, so we have AY and the total distance is 1.5 plus 0.52 plus 1, that equal to 3. Moment of 12 kilonewton is anti-clockwise about the point D, so we have minus 12 and the perpendicular distance is 1.5, so we have 12 into 1.5. Then force 8 kilonewton at point E will make a clockwise moment and distance equal to 2. Since it's a clockwise, we have positive value of moment, so we have 8 into 2 must equal to 0. 16 and this one is 18 and we have AY will be equal to 2 by 3 kilonewton. That is the only required value because we can cut at C and we can develop the FBD of the beam ABC and then we'll find out the moment at point C. So right now we have AY is equal to 2 by 3 kilonewton. So let's consider here ABC beam. We have to show the vertical reaction at point A, that is the value of AY you have to show is 2 by 3 kilonewton. The distance between AB is same as equal to 1.5 meter and the distance between BC is equal to 1 meter. At point B, we have vertical force is acting, that equal to 12 kilonewton. So this value is same as equal to 12 kilonewton. Since there is no change in the loading from B to D, the shear force on the left side and the right side is remains same. So we'll assume here that we have shear at point C equal to VC and we'll take a anti-clockwise moment, that equal to MC. This value of MC we have to find out. Since we have assumed here the value of MC is anti-clockwise, so what we'll do, we'll take a sum of moment of all forces about the point C and we'll assume here anti-clockwise positive. So purposefully we'll make it positive, and if the answer is positive, it means that this direction is correct and this sum must equal to 0. 2 by 3 multiplied by 2.5 will make a clockwise moment will be negative, so we have minus 2 by 3. Perpendicular distance is equal to 2.5. 12 kilonewton will make a clockwise moment, so we have plus 12 multiplied by the distance equal to 1, and this value of MC we have shown positive, so you have to use the positive value. Anti-clockwise is positive. Solve this, you will get the value of moment at point C. If the answer is positive, assumed direction is correct, otherwise it's a case of hogging. So here we are getting the bending moment at point C is equal to minus 10.33. It means that our assumption is wrong, is kilonewton is meter. So this one is a case of hogging. We'll continue our answer of MC as a negative value. In general, the bending stress, that is sigma b, which is a function of y, is given as minus m, that is the bending moment multiplied by y divided by I. To calculate the value of bending stress at point P, so we have sigma p, that is at point P top fiber, is equal to minus m multiplied by y of point P divided by I. So we have sigma p, that is the bending stress at point P, is minus m value is 10.33, so we have 10.33 into 10 to the power 6, that will be Newton mm. Value of yp is taken as positive is 100 divided by, for rectangular section we have moment of inertia is bd cube by 12, out of that b is equal to 100 and the depth is equal to 200. So we have 200 cube and 12 will shift in numerator. Now because of the negative value of m, this m is negative, it will become positive value. It means that we have tensile stress on the top fiber. So we have sigma p will be equal to, is 185, is a positive value, is megapascal. So this value will be tension. Now if we have a tensile stress on the fiber P, then we have compressive stress on fiber Q, because Yp and Yq are same value. So directly I will write down here the stress on Q will be compressive is 185 megapascal. That is compressive nature. As far as the distribution is considered, at point P we have tensile is 185. So suppose this value represents here 185 megapascal. Same value will be repeating here on the bottom, but is a compressive value, is also equal to 185. So this one is point P and this one is point Q. So this figure represent here the bending stress distribution in the rectangular section. A cantilever beam of length equal to 2 meter having a cross section, which one is rectangular with base is equal to 40 mm and depth is equal to 60 mm. This beam is failed by applying a force of 5 kN at the free end. The bending stress at the failure in Newton per mm square we have to find out. We know that in a case of a cantilever, the maximum value of a bending moment will occur at fixed end, and we'll show here the reactions. Let's here VB represent the shear force at point B. The moment due to 5 kN at point B will be anti-clockwise. So we'll show here reaction as a clockwise. It means that it's a case of hogging. So let's say this reaction equal to MB. So this one is a straightforward. So we're not going to write sigma m and everything. So we have bending moment at point B will be same as equal to 5 multiplied by 2. This value will be equal to 10 kilonewton meter and is clockwise. Clockwise value you have to take as a negative value, is minus 10 kilonewton meter. So this one is representing a case of hogging. We have given a rectangular section and the width is given as equal to 40 mm and the total depth D is equal to 60 mm. So this symmetrical stress will develop at top and bottom, let's say point C and point D. This one is the position of centroid, which one is the axis of symmetry. This axis is same as our Z axis and this axis is same as our Y axis. So distance of YC from the centroid is given as 60 divided by 2, that equal to positive 30, and below G you have to take the negative value. So distance of YD will be equal to D by 2, that is equal to minus 30. Bending stress sigma B is equal to minus m divided by I multiplied by y. Here m value is negative, so negative and negative will become positive, and therefore at point C, Yc is positive, so we have tension at point C. So we have sigma B maximum at point C will be equal to minus m I multiplied by Yc. Same compressible stress produced at point D also. So we'll calculate here one value, that is minus of m. Minus minus become plus. Value of m is equal to 10 into 10 to the power 6. Value of Yc is equal to positive 30 divided by BD cube by 12. This time we have width is equal to 40, depth equal to 60. So we have 60 cube. 12 will shift in numerator. So this value will come out to be 416.6 megapascal. So this one is the bending stress at failure. Same value of bending stress maximum will be in compression also. So this one is compression is minus 416.6 megapascal. In case of rectangular section, the tension and compression value are equal in magnitude. A beam of a square section 200 mm by 200 mm is fixed as a cantilever of a span equal to 3 meter. The UDL can be applied throughout the length of the beam. If the maximum stress is not to exceed 5 megapascal, then you have to calculate the value of UDL. Express your answer in kilonewton per meter. So we have given here cantilever beam. So let's represent here AB is a cantilever beam, and we have span L is equal to 3 meter. And we have a square section. The value of B is same as equal to D is same as equal to 200 mm. So exactly at this point we have centroid that equal to G. The top fiber and bottom fiber is same distance here, that equal to D by 2 and D by 2. So the compressive and the tensile stress maximum value will be either top or bottom. DL that equal to W is kilonewton per meter is same as Newton per mm. Already we have shown this equation. Is maximum at point A, that is at fixed support. So we'll convert this UDL into point load and we'll calculate what is the maximum value of bending moment at point A. So if we convert this UDL into point load, we'll get this value is a W into L, and this distance is same as L by 2. Now the force is acting in a downward, so we assume here a shear force acting at point A is vertically upward, and the moment of this point load, that is the equivalent of UDL, is clockwise, so we assume here anti-clockwise. So this one is the moment at point A. So this one is a straightforward calculation. We have bending moment at point A will be same as the product of force, that equal to W into L, and we have length equal to L by 2. So this one is the maximum possible value of bending moment. We have W into L square divided by 2. So the C represents here the distance of the top fiber and the bottom fiber from the neutral axis. In this case we have value of C is same, that equal to D by 2. Maximum bending stress is given this time, so we have maximum bending stress sigma max is same as equal to M into C divided by I for square section. So in this case we get sigma B maximum. Bending moment time is replaced as WL square divided by 2 multiplied by C divided by I. Maximum bending stress is known to us, that equal to 5 megapascal. So we have 5. UDL you have to calculate. Length is same as equal to 3 meter. 3 meter is 3000 mm. And you have to make a square of 3000. Value of C is D by 2. And we have D is equal to 200. So we have 200 divided by 2. Divided by 2 times. And the moment of inertia for square section is D to the power 4 by 12. That is, we have 200 to the power 4 and 12 will shift in numerator. Now we can solve this and we can find out the value of UDL. So we'll get the value of UDL equal to 1.48 kilonewton per meter is same as Newton per mm. A homogeneous simply supported prismatic beam of width equal to b, depth equal to d, span equal to l is subjected to constant load of magnitude equal to p. The load can be placed anywhere along the span of the beam. The maximum flexure stress developed in the beam you have to find out. In the case of simply supported beam, if we place the load, that is a constant load, exactly at the center, then the maximum deflection will occur, and hence we have maximum bending stress will occur at exactly at the center. So let here place the load is equal to F exactly at the center. So this distance is same as L by 2, as well as this distance also L by 2. Because of symmetrical loading, we have reaction at point A will be equal to F by 2, and the reaction at point B, which one is the roller support, is also equal to F by 2. So let's consider we have point A and point B. At point A, we have vertical load acting is equal to F by 2. So we have shear force is equal to F by 2. Between A and C, no load is acting, so shear force is remain constant. At point C, we have vertical load acting is F. So we have to move vertically downward by F. So finally we have minus F by 2. Between C and B, there is no load acting, so shear force is remain constant. And with the reaction at B, which is equal to F by 2, will finish at point B. This distance is same as L by 2, as well as this distance also equal to L by 2. Shear force will change the sign at point C. So at point C, we have maximum value of a bending moment. So both these rectangles here of equal area. Where the shear force will change the sign, that will be the maximum bending moment. Maximum bending moment will be at point C. Bending moment at point A will be 0. Bending moment at point B will be equal to 0. If you have a rectangle, then we'll get a triangle. So in the case of simply supported beam with the load at the center, the maximum value of a bending moment will be equal to F by 2 L by 2 is same as FL by 4. Now instead of F here, we have to use the symbol P. So maximum bending moment here will be equal to P into L by 4. And we have given here a rectangular section, width is equal to B and depth is equal to D. And we have to find out the maximum flexural stress. So let's consider here a rectangular section of width is equal to B, depth is equal to D. This one is a neutral axis, same point will represent our centroid. This value is same as the distance C, that is the distance of a top fiber from neutral axis is C, is D by 2. This also is the distance of C, that is the bottom fiber and top fiber from neutral axis at equidistance, and this value of C you have to take as D by 2. Maximum bending stress sigma B maximum is always given by bending moment M multiplied by C divided by I. In this case, the maximum value of a bending moment you have to select is PL divided by 4. Value of C is same as equal to capital D by 2. So we have capital D by 2. And the moment of inertia is BD cube by 12. So we have B into D cube and 12 will write in numerator. So this one is 4 and 12. So we have 3 in numerator and one of the D will be get cancelled. That is the square term is left. In the case of simply supported beam, the load at center, the maximum bending stress will be equal to P multiplied by L. These 3 will come in numerator divided by 2 B, that is the width, multiplied by D square. 3 times PL, 3 times PL, 2 times BD square, 2 times BD square, choice D is correct. A simply supported beam square in cross section is subjected to uniform downward load of W equal to 90 kN per meter is same as 90 Newton per mm on a span of L equal to 4 meter. The allowable stress in magnitude in tension and compression is given as 150. Find the dimension of the cross section of the beam that may be used for this application. So we have simply supported beam here and we have total load equal to W into L. So this total load will be equally divided into the two support and we have equal reaction at A and B. So in this case the reaction at point A, AY, is same as the reaction at point B, which means the roller support, and is equal to WL by 2. So this time we have AY is same as equal to BY is same as equal to W into L by 2. So first we find out here the maximum bending moment. For this one, we'll construct the shear force diagram of the beam AB. Let's say the center point equal to C. So we have shear force at point A is WL by 2. Total load is acting downward is W into L. So finally we have to show here a rectangular load into triangular shear force, and this shear force at point B is minus WL by 2. With reaction at point B, you have to close it, and this distance between A to C is exactly L by 2, L by 2. If the SFD is a triangle, then we will get here a parabola. In the case of bending moment diagram, maximum value of bending moment is at point C, which one is same as the area of the triangle. So bending moment at point C is the maximum value, and this maximum value is same as equal to 1 by 2 multiplied by UDL W into L square divided by 4. WL by 2, L by 2 is WL square by 4 is 1 by 8 WL square, and we have given here square section, so B is same as equal to D. The maximum stress will occur either on the top fiber or bottom fiber. So both this top fiber and bottom fiber distance equal to C is equal to D by 2. Maximum stress sigma B maximum is given as the maximum value of a bending moment M multiplied by C divided by I. Maximum value of a bending stress is given as 150 megapascal. So we have 150. M value is given as WL square by 8. So we have WL square divided by 8 multiplied by C divided by I. So we have 150. UDL value W is same as 90 Newton per mm. So we have 90. Span length L is given as 4, that equal to 4000, and we have to make a square of it divided by 8 multiplied by C. C is same as D by 2. So we have D by 2. And for square section, moment of inertia is D to the power 4 by 12. So one of the D will be get cancelled here, and we are left here D cube, so we can calculate the value of D. So in this case, you will get the value of D equal to is approximately equal to 193. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.